Hi, this lesson is all about optimization, a quick introduction to the concept, and then how do we write linear programming. So we've been talking about multiple regression, and this is a completely different type of model. So linear programming is this really awesome math model that helps us allocate resources, which could be people or materials or ingredients, equipment, money, something in the most optimal way. So we will be trying to maximize something or minimize something. The applications are very broad. There's all kinds of really awesome stuff that we can do. We'll go through a lot of these different examples. Your project will focus on inventory control. We will do ones on product planning and routing and distribution scheduling and how do we do that, potentially employee scheduling. There's all kinds of really awesome uses for optimization. Here's the basic concept and process that we are going to go through. Step 1, describe the problem and their objective. So this will start as a word problem. And how do we actually flesh out all of the different pieces? So you have to figure out what are each constraint, what are the decision variables. So here DV means a different thing than regression. Similar but totally different ideas, so keep that in mind. Then we will write the objective with the decision variables, write the constraints with the decision variables, add non-negativity constraints, and put it all together. So the first thing is trying to understand the problem. What is their goal? What are they trying to do? What is the scene that we are setting? What are the variables involved? There's going to be a lot of different variables and understanding which is which. What are they trying to do? So are they trying to maximize? Are they trying to minimize? And then what else do we need to consider? So what are other constraints and things that are happening that need to be considered? Take a minute, make sure you understand these because that is so important in writing these equations. So equal to means that it has to be 100% equal to. There is no wiggle room. We can say more than, in which case it cannot be equal to, it has to be more than. We can say more than or equal to, in which case we could meet that requirement or be more. And of course the opposite. So less than or equal to, we could meet that or be less than that, and we would still be okay with our requirement. So here's what these look like. And yes, they are kind of scary to look at first. So we're going to maximize something, probably profit. And then it's going to equal some constant. So you can think about beta zeros. We're going to insert a number here times whatever variable this is, plus another constant times another variable, plus as many of these as we want to. We're going to start with 2, and then we're going to be adding quite a bit more. And this equation is subject to some constraints about it. So there are certain things that have to be met in order to make this work, or make that be true in the problem that we're considering. So this is maximize, this is minimize. So I'm just going to flip back and forth, and what do you notice? Oh, it has something to do with those arrows. So we'll keep that in mind as we go. Got it? Probably not. The only way, in my opinion, to really understand this is to practice and practice and practice and practice. And then by the third lesson, you're going to be so sick of it that you will just know it. So here's our first example. This is the example in the book that we are using. So fuel and solvent. A company produces 2 products, a fuel additive and a solvent base, from a combination of 3 materials. Each material is limited by availability. We only have so much of them to make the big products. Fuel gives us $40 a ton profit. Solvent gives us $30 a ton profit. And we have to get rid of anything due to spoilage, so we want to find the best solution so that we're not wasting our materials and we are maximizing the highest potential profit. So our problem is that we don't want to waste things. We're trying to make as much of the products as possible and making the most profit possible. So we have to describe the objective, maximization, describe each constraint. So we have a couple different constraints here. We have different amounts of materials that are needed for each product. So for fuel, we need certain things. For solvent, we need certain things, which I'll show you in a minute. We have different amounts that are available of those three materials. And our decision variables is going to be how much fuel do we make and how much solvent do we make. So I'm just going to name those F and S. You could name them A and B. You could name them X1, X2. Doesn't matter, but for the ease, I'm just going to say fuel, F, solvent, S. So to make the first equation, I'm going to look back at how much profit I'm making for each. So to maximize my profit, it's $40 a ton, $40 for every fuel ton I make, and it is $30 for every solvent ton that I make. So 40 and 30 are my constants. And then I have to write the constraints. So the first thing that we will do is put it into some kind of a chart. I like the decision variables to go across this to the side, to the top, and then down the side, I like to have all of your materials or constraints. So in this case, fuel needs 0.4 tons of material 1 and 0.5 tons of material 2 of solvent. I'm sorry, for material 1, this is what is needed for each one. And we only have 20 tons available of material 1. So material 1 is constrained because we have to account for both things we're making. So we have to use 0.4 tons for fuel, 0.5 tons for solvent, and then the max that we can use is 20. We cannot use all of it, but we can't use more than that. So that's constraint 1. Constraint 2, material 2 is constrained. We don't have anything used for fuel, so the only thing being used is solvent. And we go across here and we find that we only have 5 available. So that's our constraint for 2. For 3, same thing. We're just going to go straight across the chart. If you organize it like this, you just go straight across. So 0.6 for fuel, 0.3 for solvent, and we only have 21 available. We're going to add a non-negativity constraint. When we solve this graphically, I'll show you why we're doing this. But essentially, we don't want to make negative fuel tons and negative solvent tons. Making negative product doesn't make sense. So this just makes our axes a constraint as well. So we put it all together, and this is what the model looks like. So we have our profit equation that is subject to all of these different constraints. This is as far as we're going to go for this video. The next video, we'll talk about how we actually go about solving these. And don't worry, Excel does it for you. So we're going to spend some time practicing. So pause, look at the puck and pawn, and read through this. So press pause, read through it. First step is that we organize it into a chart. So again, we're going to say hockey sticks and chess sets are our 2 decision variables. And then I have my profit right here for each one. And then I have my constraints, A, B, and C. I also have my maximum capacity going through there. So step 1, again, pause the video and see if you can fill these in. Pause. Okay. So the objective here is to maximize profit of hockey sticks and chess sets. We have different amounts of time that is needed to make each product, and we have different available hours at each machine. Not all products need all machines, so there's all kinds of differing constraints here. The decision variables, in my opinion, let's just use H for hockey sticks and C for chess sets. So for every hockey stick produced, the company makes $2. For every chess set, the company makes $4. So write your decision variable objective. Pause. So our max profit would be 2H plus 4C. And again, all I'm doing is saying 2 times every hockey stick I make and 4 times every chess set I make. So if I make 10 hockey sticks and 4 chess sets, I can solve and figure out what would be my maximum profit for the day. Go ahead and pause again and work on writing your constraints. So there's 3 constraints for machine A, B, and C. So pause and write those. So for machine A, I have 4 hours needed for each hockey stick. I have 6 hours needed for each chess set, and I have a maximum of 120 hours. I don't have to use all 120, but I can't go over 120. Same for machine B. 2H plus 6C cannot be more than, but it can be equal to 72. And then here, I don't have anything for H because I don't need machine C for hockey sticks. We again are going to add non-negativity constraints because we don't want to make negative hockey sticks. That makes no sense. We write it out and we're good to go. So again, pause the video and I want you to work through this one. The same concept, we're making sandals and boots, except this time we want to minimize cost and we have a minimum amount of hours that we have to use. So we have to use these or more, and that is our minimum cost. So pause and work through writing this equation. Yours should look just like this. So again, I use sandals, S, boots, B, and we go through and you will notice that since they are minimum requirements, the arrows have changed. There are some assumptions in linear programming that I want to quickly discuss. These assumptions are not like regression that we test them. These are just assumed within the entire concept. So first of all, we have to have limited resources. We cannot have infinite amounts of everything. There are finite requirements, whether that's workers or equipment or materials or whatever it is. There's also a very explicit objective, maximizing or minimizing. We can't do both. We'd have to run separate ones if we're trying to understand both of them. There is an assumption of linearity. So all of those equations are linear relationships. We're not looking at exponential relationships or anything else to that effect. There is also this huge assumption of homogeneity. Meaning, if I am working on one machine, A, and my friend is working on another machine, A, we are assuming that we are both identical in our productivity and that both machines are working identically. So the productivity and the way that everything works is assumed to be the same, even though we really know that some people are more efficient, some machines might be newer versus older. We are just making that huge assumption. And we are also assuming divisibility. So we can actually take these big ideas and break them down into fractions. So parts of a whole. So I want you to take a moment and go to your book and practice questions 23 through 27. The answers are posted in Canvas. But in your book, the optimization chapter 7 is not in the main book. It is in the very, very, very back. Think appendix, and then behind that, we have added 2 to 3 chapters behind it. So check this out, and I will see you next time. And of course, you do have to finish homework 1. If you have not finished that already, make sure you do. If you want to start working ahead, you can look over project 2. Don't panic, I will get you there. It looks a little overwhelming. And then you can enable Solver in Excel. This is done the same way as data analysis tool that we added in, except now you're going to click Solver.